For the first time, NASA has turned the silence of space into something eerie, a real sound coming from a black hole 240 million light-years away. Scientists used a special process to capture this phenomenal sound. But the real question is this just a natural phenomenon, or is there something more? Whatever it is, the sound of the void has never been heard like this before. Listen closely. Because space might not be as silent as we thought. This black hole hangs out in the middle of a galaxy cluster called Perseus, about 240 million light-years away from Earth. While it sounds like something out of a science fiction movie, it's real. And thanks to a fancy technique called sonification, what used to be an invisible signal is now a weird, eerie tune. What makes this melody unsettling is a hidden secret science is only beginning to uncover. The story starts back in 2003 when scientists first figured out that the supermassive black hole at the heart of the Perseus galaxy cluster was making ripples in the gas around it. These ripples acted like sound waves, though way too low-pitched for human ears to catch. Imagine a note 57 octaves below middle C that's so far off the usual piano range it's almost laughable. But here's where things get cool. Using data from NASA's Chandra X-ray Observatory, those waves got cranked up by tens of octaves until they landed in a pitch range humans could finally hear. Now, about those waves. The black hole sends out pressure waves which move through the cluster's gas and create a sort of cosmic hum. Normally, space is too empty for sound to travel, but galaxy clusters are packed with hot gas, making it possible for these pressure waves to ripple outward. Scientists took these ripples and mapped them into something we can listen to by shifting their pitch way up. Think of it as taking a really deep bass sound and speeding it up until it's high enough for human ears to detect. To picture what's happening, imagine a radar sweep. The sound you hear changes depending on where the sweep points, because different areas around the black hole give off different frequencies. When scientists scanned the data, they could turn each bit of information into a sound. The result? An audio clip that's both haunting and fascinating. But Perseus isn't the only black hole getting the sonification treatment. Scientists also looked at Messier 87, or M87, home to another famous black hole. This one hit the spotlight in 2019, when the Event Horizon Telescope project dropped the first ever image of a black hole. This time, though, the sound project didn't use that data. Instead, it pulled info from other observatories that caught Messier 87's action on a bigger scale. They used 3 types of data, X-rays, optical light, and radio waves, to create a layered soundscape. Here's how it works. X-rays collected by Chandra give off the highest pitched tones. Optical light from the Hubble Space Telescope falls in the middle range, and radio waves recorded by the Atacama Large Millimeter Array hit the lowest notes. Together they create a strange melody that shifts as the sonification scans across the image. The brightest spot in the image, where the black hole lives, ends up being the loudest part of the audio. And do not forget the jet. Messier 87's black hole is famous for shooting out a massive jet of energy and matter. That jet shows up in the sonification as a structure to the upper right of the image, and the sound changes as the scan moves over it. This is not just a cool audio effect. It's a way to experience what's going on in space through a totally different sense. This whole sound experiment is part of a larger project by NASA's Universe of Learning, which aims to make space science more accessible. The folks behind it include experts from the Chandra X-ray Center, NASA's Goddard Space Flight Center, and the Hubble Space Telescope team, with help from a musician and an astrophysicist from System Sound. Together, they've been turning complex space data into soundscapes that anyone can explore. Sonification helps scientists and the public connect with space in new ways. Turning data into sound lets researchers notice details they might miss by just looking at images. Plus, for people who are visually impaired, it offers a way to experience space discoveries without needing to see anything. Let's circle back to the Perseus cluster for a second. This is not just any galaxy cluster. It's one of the most massive structures in the universe. Inside it, there are hundreds, maybe thousands of galaxies, all surrounded by superheated gas. That gas acts as a medium for sound waves, making it possible for us to hear the black hole's activity after some major audio tweaking. Meanwhile, over at Messier 87, the black hole there is a heavyweight champion, tipping the scales at about 6.5 billion times the mass of our Sun. When matter falls into this black hole, it gets superheated and emits energy that can shoot out in powerful jets. These jets stretch for thousands of light years, and they're one of the reasons Messier 87's black hole has become such a superstar in the astronomy world. Both the Perseus and Messier 87 projects show how sonification can turn space science into something more relatable. It's one thing to see an image of a galaxy or a black hole, but hearing it, that's a whole different experience. It taps into the human sense of curiosity in a way that visuals alone cannot always do. This sound-making journey has been in the works for years, and it's still going strong. The team behind it is constantly finding new ways to turn space data into sound. They're exploring everything from star clusters to supernovae, translating the universe's light show into a cosmic concert. Every sonification adds a new piece to the puzzle, helping scientists and space lovers alike experience the universe in a fresh way. For now, the Perseus and Messier 87 black hole sonifications stand out as some of the most striking examples. They do not just reveal the hidden sounds of space. They remind us how much more there is to discover and how different senses can help unlock the universe's secrets. To dig deeper into this project, you can visit NASA's A Universe of Sound website, where more sonifications and details about the process are available. This website features a growing collection of sonifications from various cosmic sources, including nebulae, star-forming regions, and exploding stars. Each sonification is crafted by combining data from different telescopes and adjusting the frequencies to fit within the human hearing range. What makes the Perseus and Messier 87 sonifications stand out is the sheer scale of what they represent. The Perseus cluster spans millions of light years and contains countless galaxies, each with billions of stars. Meanwhile, Messier 87's black hole alone has a mass of over 6 billion suns, making it one of the largest black holes ever discovered. The sounds we hear from these objects give us a sense of the immense forces at play in these distant corners of the universe. These sonifications are not created randomly. Scientists start by selecting specific types of data, like X-rays, visible light or radio waves, collected by different observatories. They then assign each type of data to a particular sound range, with higher energy data like X-rays corresponding to higher pitch tones and lower energy data like radio waves corresponding to lower pitch tones. The result is a soundscape that reflects the underlying structure of the cosmic object being studied. In the case of the Perseus cluster, the sonification process involved extracting sound wave patterns from the X-ray data collected by the Chandra X-ray Observatory. These sound waves were originally too low in frequency for human ears, so scientists had to scale them up by dozens of octaves to bring them into an audible range. The resulting sound is a low, rumbling hum that varies in intensity depending on the position within the cluster. For Messier 87, the sonification team used data from multiple sources, including the Hubble Space Telescope and the Atacama Large Millimeter Array. By combining data from different wavelengths, they were able to create a layered soundscape that captures the complex activity around the black hole. The sound changes as the sonification moves across the image, reflecting variations in brightness and energy levels. One of the most fascinating aspects of these sonifications is how they reveal patterns that might not be immediately obvious in visual images. For example, in the Perseus cluster sonification, the changes in pitch and volume highlight the distribution of hot gas and the pressure waves created by the black hole. Similarly, in the M87 sonification, the variations in sound intensity draw attention to the powerful jet of energy being emitted by the black hole. These sonifications have also opened up new opportunities for collaboration between scientists and artists. Musicians and sound designers have been working with astronomers to create compositions based on the sonified data, blending science and art in innovative ways. This interdisciplinary approach has helped to engage a wider audience and spark interest in space science among people who might not otherwise have been interested. Beyond their artistic value, sonifications are proving to be valuable tools for scientific research. By converting data into sound, scientists can detect subtle variations and patterns that might be difficult to spot visually. This approach is particularly useful for studying complex systems like galaxy clusters, where multiple factors interact in intricate ways. What did scientists find on these icy worlds? Year 2 rolled around, and NASA's scientists were still on a roll with the James Webb Space Telescope. But things got tricky when it came to Jupiter's moons. Not as many jaw-dropping snapshots of the solar system came through compared to Year 1, but some wild stuff did pop up. To kick things off, they turned its gaze toward Jupiter's biggest moon, Ganymede. This massive ice-covered moon, with its frozen shell and possible hidden ocean underneath, was already on everyone's radar for its potential geysers spewing material into space. Researchers had tons of questions about what exactly was happening on its surface, so they went looking for hydrogen peroxide, a result of charged particles smashing into Ganymede's icy exterior. Turns out, Jupiter's magnetosphere and solar wind particles are constantly bombarding Ganymede, breaking down surface molecules and creating clouds of hydrogen peroxide. The observatory mapped out where these clouds were forming, giving a clearer picture of how all these charged particles are interacting with the moon. After that, they swung the instrument toward Io, the most volcanic body in the solar system. What they found was sulfur dioxide spewing from specific volcanoes. By comparing this data with images from Juno, they got a sharper view of how Io's volcanic activity fits into its chaotic environment. Next up was Europa, another icy giant known for its potential subsurface ocean. Scientists are dying to know how much interaction there is between the ocean and its icy crust. The telescope managed to spot carbon dioxide in specific regions of Europa, which was a huge deal, because carbon dioxide shouldn't hang around on the surface of an icy world without some process constantly renewing it. No, it's not space whales shooting out carbon dioxide, but there's a good chance it could be geysers. Sadly, no geyser activity was caught this time around. Moving farther out, Uranus got its moment in the spotlight. Last year, the observatory gave us one of the most liked images of Uranus, and this year it delivered an even crisper shot. The planet, known for being tilted completely on its side, had its rings on full display. What made this image special was the faint zeta ring showing up, something that wasn't visible in previous shots. Capturing these images wasn't easy since Uranus spins rapidly, completing a full rotation in about 17 hours, but the equipment handled it like a pro. This confirmed its ability to capture fast-moving objects in our solar system. With the solar system section wrapped up, things moved on to exoplanets. One of the primary goals is to figure out what's going on with exoplanet atmospheres. It does this by watching planets pass in front of their stars, picking up the faint light filtering through their atmospheres to determine what chemicals are present. Among the standout observations was the TRAPPIST-1 system, home to 7 Earth-sized planets. Scientists were especially curious about whether these planets had atmospheres. Sadly, the news wasn't great for TRAPPIST-1b and TRAPPIST-1c. Both seemed to be barren, airless rocks without a hint of an atmosphere. This wasn't totally shocking, considering the intense radiation and solar flares from their star likely stripped away any atmospheres they might have had. The hope now lies with the outer planets in the system, but we'll have to wait longer for results on those. Right now, it's anyone's guess whether they have atmospheres or not, though odds aren't looking great given the harsh conditions around red dwarf stars. Shifting gears to something even more out there, a potential exomoon around a brown dwarf. Brown dwarfs are essentially failed stars, not massive enough to sustain hydrogen fusion. The observatory picked up something intriguing when it detected methane in a brown dwarf's atmosphere, which is odd because methane usually gets destroyed at the temperatures found there. One possible explanation? A temperature inversion caused by something heating up the brown dwarf's outer layers. Even crazier, the brown dwarf showed auroras, despite having no nearby star to supply a solar wind. This led to speculation about a moon orbiting the brown dwarf, which could be generating the auroras by interacting with its magnetosphere. If confirmed, this would be the first solid evidence of an exomoon. Then there was the dust-up around Beta Pictoris, a young star system about 63 light-years away. Decades ago, Spitzer detected a cloud of dust around the system, which astronomers thought could either be from constant grinding between small particles or a one-time asteroid collision. The Space Telescope revisited the system and didn't find the same dust cloud, which points toward the latter explanation. It looks like Spitzer might have caught the system during an asteroid smash-up, a rare and fleeting event. What new clues about distant worlds might reveal more about life beyond Earth? Finally, let's talk about Hycean worlds, a new type of planet that's been theorized recently. These are planets with thick hydrogen atmospheres covering liquid water oceans, potentially expanding the habitable zone concept. One promising candidate, K2-18b, sits about 120 light-years away. This planet, about 3 times Earth's size, showed signs of methane and carbon dioxide in its atmosphere. Even more exciting, there was a faint signal of dimethyl sulfide, a chemical mostly produced by life on Earth. Before you get too excited, though, it's worth noting that detecting this chemical in such high quantities would require life to produce it at 20 times the rate seen on Earth. Other teams suggested alternative explanations, including a lava world scenario or a mini Neptune with a thick atmosphere. The debate is still raging, with no clear consensus on whether K2-18b could host life, or if it's just another strange, lifeless world. For now, it remains one of the most intriguing targets for future observations, with everyone eagerly awaiting more data to settle the matter. Continuing with exoplanet studies, there's more about the TRAPPIST-1 system that's worth mentioning. While the innermost planets didn't show atmospheres, astronomers are still holding out hope for the outer planets, especially TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g. These planets are located in the so-called habitable zone, where conditions might allow for liquid water. The observatory's precision in detecting chemical signatures means that, if there is even a thin atmosphere present on these worlds, scientists will eventually find it. Another big topic for Year 2 was asteroid collisions. Astronomers have long been fascinated by how asteroid belts evolve and interact in young star systems. When the instrument turned its attention to the Beta Pictoris system, the lack of dust, this time compared to decades ago, gave strong support to the idea of a massive asteroid collision occurring in the past. This kind of event helps scientists understand how planets form and grow in their early stages, as these high-impact events are believed to play a crucial role in shaping planetary systems. Farther away from our own neighborhood, it also focused on gas giants in other star systems. While our solar system has 4 well-known gas giants, astronomers have discovered countless more around distant stars. Its ability to analyze the light passing through the atmospheres of these massive planets has provided insights into their chemical makeup. For example, several gas giants observed showed unusual levels of carbon monoxide and water vapor, hinting at complex atmospheric processes. One of the most exciting finds was a planet that appears to be undergoing atmospheric loss. This happens when intense radiation from a nearby star strips away the outer layers of a planet's atmosphere. By studying these processes in detail, scientists can learn more about how planets evolve over time and how some might lose their atmospheres entirely, turning from potentially habitable worlds into barren rocks. On the topic of moons, distant planet observations have raised the possibility of finding exomoons in other systems. While the potential exomoon around a brown dwarf remains unconfirmed, it has sparked renewed interest in the search for moons beyond our solar system. Moons play a critical role in stabilizing planetary environments, as seen with Earth's moon, and finding them around exoplanets could significantly impact our understanding of habitability. Another area where the observatory has excelled is in the study of star formation. Young stars, surrounded by thick clouds of gas and dust, are prime targets for understanding how solar systems come to be. In several regions of active star formation, stunning images of protostars and their surrounding disks were captured, offering a glimpse into the earliest stages of planet formation. One of the more surprising discoveries came from a star system that showed signs of forming giant planets much farther from the star than expected. This challenges existing models of planet formation, which typically place giant planets closer to their parent stars. The data collected is forcing scientists to rethink how and where planets can form, opening up new possibilities for the types of planetary systems that might exist. The observatory's observations of distant galaxies, one particularly interesting find was a comet that appeared to have an unusual amount of carbon dioxide in its coma, suggesting that it might have formed in a different region of the solar system than most known comets. Finally, the search for potentially habitable worlds remains a top priority. While no definitive evidence of life has been found, the detailed study of atmospheres, surface conditions, and potential biosignatures continues to drive scientific inquiry. What if our search for extraterrestrial life ends not with discovery, but with proof that Earth is the only cradle of life? Share your thoughts below, like and subscribe.